Welcome to this lecture on the properties of determinants. So, this is the second lecture in this series on determinants. Previously, we had talked about the definition of determinants and some of the areas, some of the instances where it comes up. Next, we are going to talk about the properties of determinants. Properties of determinants. So, the idea behind trying to calculate the properties of the determinants is just like with any other property that we may have seen, for example, the distributive property of multiplication. The main idea is to add to what we already know from the definition by trying to say, okay, can we simplify the computation of certain quantities. So, what we want to do is to say, okay, we know the definition of a determinant, but can we come up with some properties which will simplify or make more efficient the process by which we compute these determinants. For example, if you think about the distributive property that you have three scalars a, b and c, and then you say that okay, a times b plus c, the sum b plus c is nothing but taken the sum individually a times b plus a times c. Now, even though this is something which follows from the definitions of multiplication and addition, what we can see, and we will just shortly write it down, is that the idea is that in one way one is able to compute the same quantity in a more efficient way. So, what I mean is the following. So, the idea is as follows. So, consider three numbers a, b, c, which are, let us say, scalars. We know that a times b plus c is equal to a times b plus a times c. So, these two are equal. So, in principle, given any three numbers, either we can compute using this or we could compute using this, but there is a little bit difference in the efficiency in the two processes. So, for example, if we compute using this way, we have one multiplication that we have to do and we have one addition that we have to do, whereas on this side we have to do two multiplications and one addition. So, even though these are the same quantity, we have to apply different amount of effort. So, same quantity, but different effort. So, that is the idea behind looking at these properties of the determinants. Using the definition of the determinant, we can anyway calculate the determinant, but by exploiting some features in the determinants, the definition, we can come up with some simplifying principles, which are of course not only useful when we try to compute the determinants, but also when we want to make a computer evaluate certain determinants, especially when the size of the square matrices for whom we are interested in calculating the determinant, it becomes larger. So, that is the basic idea of looking at the properties of the determinants. So, we will start by looking at the properties and try to verify the properties using some examples, try to get an idea of why certain properties make sense and so on. Okay. So, properties of determinants. So, we will start off by just noting certain simple determinants, the values of determinants of some simple matrices. The idea would be that okay, if we can identify certain matrices or certain kinds of matrices which have relatively simpler determinant calculations, then what we could do to calculate the determinant of a more relatively complicated matrix is to try to bring it closer in the form using these properties. So, the first property or the first relatively easy determinant that we can notice is just coming directly from the definition, and that is that if you have a square matrix with an entire row of zeros, okay, then what would be the determinant of that matrix? It would be nothing but 0. Why is that? because just from the definition, if you expand along the row which has 0 entries, the sum of the products of the entry of the row and its corresponding cofactor, each of them will be 0, and so the overall determinant would be 0. So, the first property that we can write down is that if the entire row of a determinant is 0, okay. So, excuse me, this should be if the entire row of a square matrix is 0. Then the value of its determinant is also 0. So, what we are trying to say is that if the entire row of a square matrix is 0, then the value of the determinant is also 0. Now, as we had seen in the definition of a determinant, it is not just that we can expand the square matrix along a row, but we can also do it along a column. And so, in completeness, this property should read if the entire row or column of a square matrix is 0, then the value of the determinant is 0. So, let me just make that addition here. So, I say that if the entire row or column of a square matrix is 0, and this kind of an interchangeability between the row and the column is something that we will see in other properties as well. So, it is good to make note of it here. And now, let us just look at a 2 by 2 matrix to see how this works out. So, if the example that we consider is a 2 by 2 matrix which has 2 0 entries C D, then either we take the determinant using the definition or the formula that we know, that this is this entry times this entry minus this. In either way, we can get that if we expand along this row, it is 0 times something plus 0 times something else, and because each of them is 0, the sum is 0. And one can imagine doing this for a general n by n square matrix. Just expand along a row or expand along a column. If it is entirely 0, then the value of the determinant is going to be 0. Okay. So, this is a simple property, but something that is good to make a note of. Okay. So, the next property that we want to talk about, property 2, the property 2 also has a similar flavor, and the idea here is that if you have a diagonal matrix. So, recall a diagonal matrix is a matrix which has elements only along its diagonal and the remaining entries are 0. So, if we look at a diagonal matrix, then its determinant is nothing but the product of the diagonal entries. So, for a diagonal matrix, the determinant is the product of the diagonal entries. And why is this the case? Well, again this follows directly from the definition, in that if you try to now expand along any row or column, what we will be left with, because there is only one entry which will be non-zero. So, that will be the only term that you get multiplied by its cofactor, which will also be have a structure similar to the structure of a diagonal matrix. So, let us just take a look at a 3 by 3 matrix example to get an idea of this. So, the example that we look at of a 3 by 3 matrix is that if you have a matrix A 1 1, it's a diagonal matrix, right. So, the off diagonal terms are 0, A 2 2, A 3 3. Okay. Now, if this is a matrix and we want to take the determinant of this, then we can expand along any row or column. So, let us for example, expand along this row. So, this is going to be equal to this entry A 1 1 times its cofactor. So, the cofactor will be obtained, remember, from the definition by deleting this entire row, this column, and then what we are left with A 2 2 0 0 A 3 3. This would be the cofactor, because the index of this 1 1 is such that minus 1 power 1 plus 1, which is nothing but 1, and then the other terms we do not have to worry about because they are zeros, because these terms are zeros. Now, what about this term? Again, either directly from the definition or by knowing the determinant of a 2 by 2 matrix, we can just write this down as A 1 1 times A 2 2 times A 3 3. So, there we have it, that the determinant of a diagonal matrix is nothing but the product of the diagonal elements. And what we have illustrated is for a 3 by 3 matrix in general, for a 2 by 2, or more generally any other kind of order n by n, we can have the same sort of property, that if you look at a diagonal matrix, its determinant, if you want to calculate it, is very easy. You just have to look at the diagonal terms, make a product of them, and that is the determinant. And to show it in general also, we could do this sort of expanding along a row or column. And again, just like for the previous property, it is good to know this, because if we have a determinant which has a something similar form like a diagonal matrix, then we know that it is going to take an easier way to evaluate the determinant, and not just for a diagonal matrix. And in fact, this is the topic of property 3, which is that if you have any triangular matrix, a triangular matrix is something which has elements only on one side of the diagonal, either upper triangular or lower triangular. But in those cases also, and by using roughly the same procedure, we can show that the determinant of a triangular matrix will also be the product of the diagonal entries. So, let me write this down. Let me write down this property. So, property 3 is that for a triangular matrix, the determinant is the product of diagonal entries. As an example, let us consider a simpler 2 by 2 example, just a matrix which has A, B, C, and there is a 0 here. So, this is in the form of a upper triangular matrix, right. And what is the determinant of this? So, the determinant of this is nothing but A times C, A times C, which is just the product of the diagonal entries. We could also look at a 3 by 3 or a general n by n example, but the idea is that if you have a general matrix, let us say in this particular case 3 by 3. So, if you have A, B, C, and in this case let us look at a 3 by 3 lower triangular matrix. So, we have zeros in these cases, and then it does not matter what is over here, it could be anything, right. So, this is the lower triangular matrix. If you would like to evaluate the determinant of this matrix, as before, we can expand along this row, because these two entries are 0. So, that is going to be A times its cofactor. So, cofactor will have b 0 dot c. So, this dot represents it could be anything. We do not need to worry about these two terms because they are 0, and then in expanding this determinant we know it is again a b c. So, again this is the product of diagonal entries. Right. So, this is again pointing out how to calculate the determinant of a matrix for which calculation of the determinant is easy, relatively speaking. So, if you have a triangular matrix or a diagonal matrix or a matrix which has a one whole row or column of zeros, then it is relatively easy to calculate its determinant. So, in these set of 3 properties, what we have just seen or just noted are broadly speaking easily calculable determinants, all right. So, next we will move on to the next set of properties. Again, just to point out over here that we could also try to discuss how these properties are related to some of the geometric ideas or the algebraic ideas that we discussed when we mentioned about the determinant. For example, if you think about a matrix, a square matrix which has an entire row of zeros, right. So, if you have let us say a 2 by 2 matrix, because that is the dimension in which we discussed about the geometry of a determinant, and one row is 0. So, what it means is that the 2 columns of the matrix are aligned along the y axis. So, basically there is no area, and that makes sense that the determinant is 0 because there is no area enclosed by the parallelogram. So, let me just briefly illustrate this idea. So, this is a small note, and that is that if you have a 2 by 2 matrix with one row as 0, and so this could be anything, let us say A and B, and then if you try to sketch this geometrically like we did in the last lecture, so this is the x axis and this is the y axis. If you think about these as the columns, the column vectors, so one is 0 A, so maybe this is 0 A, and maybe the other one is 0 B. So, what is the parallelogram over here? There is no parallelogram because these two vectors are parallel, in fact they are collinear. Therefore, the area enclosed by the column vectors is 0, and this is consistent with the determinant itself being a 0. Now, the fact that the determinant is 0, you could again calculate it directly, or you could just note from the property that okay, you have a matrix full of zeros, and so the determinant is 0. So, the main idea for just making this small note is that for the property that we just discussed, or for those that we may discuss, for some cases it might be helpful to just have a geometrical picture in mind, because it just adds a layer to our understanding, all right. Okay. So, now next we want to move to the next property. So, property 4. So, this property relates to the determinant of a matrix and its transpose. So, recall when we talk about the transpose of a matrix, the transpose of a matrix is obtained by interchanging the rows and their columns, and something which comes directly from the definition of the determinant is that they have the same determinant. So, matrix and its transpose have the same determinant. So, the property is that if we interchange the row and column of a matrix, square matrix, the interchanging the row and the column of a square matrix does not change the value of determinant. In other words, the determinant of a square matrix A. So, we are using determinant here as a notation for calculating the determinant of a square matrix is equal to the determinant of its transpose. So, A transpose is a symbol used for denoting the transpose of a matrix. So, a determinant and its transpose have the same sorry, apologies. So, the matrix and its transpose have the same determinant, and this is something that you can see for a one dimensional or a 1 by 1 square matrix. So, that is just the transpose is equal to the matrix. So, nothing new about it. For a 2 by 2 matrix also we can calculate and see this happens. So, let us look at that. So, if you look at a 2 by 2 matrix, you have a matrix A, B, C, D. Okay. What is its transpose? The transpose of this, or what we obtain by interchanging the rows and the columns. So, here A B is a row, so we can make that a column A B. Again C D is a row, we can make that a column C D. Okay. So, this one is A D minus B C is the determinant. So, the determinant of this is A D minus B C. What about here? Again the determinant of this is A D minus B C. So, here also the determinant is A D minus B C. So, these two are the same. So, you can take a transpose of a matrix and you can get the same determinant. This is for a 2 by 2 matrix. For a 3 by 3 also we can sort of verify or check how it follows from the determinant's definition, because there we say okay, we can expand along a row or a column. So, if you want to see that here, rather than calculating explicitly the value of the determinant, we could say okay, instead of expanding along the row A B, instead of expanding along the row A B here, we are expanding along this column A B, and then we see that the cofactors come out to be the same, and so the values of the determinants come out to be the same. For a more general matrix 3 by 3 also we could apply the same logic. You have the first row becomes the first column. If you expand along that, then iteratively or using induction one could say okay, because we know a 2 by 2 matrix and its transpose has the same determinant, therefore, the cofactor matrices, the matrices which form the cofactors also have the same determinant, and so on. So, we could do this for a general n by n square matrix. But the point is just, and the point to note over here is that a matrix and its transpose have the same determinant. All right. So, this is the property 4 which we wanted to talk about. Now, the next property has to do with what happens when you interchange two rows of a determinant. So, if you have a general matrix, square matrix, and you change one row and exchange it in another row, then what happens to the value of the determinant? Similarly, for a column, if you have one column and you interchange it with another column, what happens to the value of the determinant? And what we will see is that if we do this, the sign of the determinant changes. So, let me write it down and then we will see why that happens. So, the next property is that if any two rows or columns. So, again there is this kind of a duality between rows and columns, in the sense that what we say about one applies equally well to the other, and that is sort of following because the matrix and a transpose where you interchange the rows and columns have the same determinant. So, if they are interchanged, then the sign of the determinant changes. Changes. So, let me read this again. If any two rows or columns are interchanged, then the sign of the determinant changes, right. And just to see this in operation, we can consider some examples. Let us start with a 2 by 2 example. The idea would be that we will replace a row and a column and then see what happens to the value of the determinant. All right. So, in this example, and this example will also help us to just establish a notation for these changes. So, we have our 2 by 2 matrix A, B, C, D. Let us call this row 1, let us call this row 2, and the transformation that we are doing is that we are interchanging R1 and R2. All right. So, what happens when we interchange R1 and R2? Instead of row 1 A, B, we have row 2, which is C, D, and instead of C, D, because we have interchanged it with A, B, we have A, B. Now, let us calculate the determinants. What is the determinant of this? Again, as before, for a 2 by 2 matrix AD minus BC, or we could do it by expanding along a row and finding out the cofactors. So, this is AD minus BC. What about over here? Again, using the formula, we have here the first entry in the row 1 column 1 is C. So, it is actually CB minus AD, right. And if you look at these two terms, this is nothing but minus of AD minus BC. So, the sign between these two, if we compare, the sign changes. All right. So, if we interchange a row, or we could equally do it for a column, we could do it for a 2 by 2 matrix that we have seen here, we could do it for a 3 by 3, 4 by 4. In general, for an n by n matrix, we can establish over here, we have just verified, but more formally also this can be said that if you just interchange the rows and the columns, then the sign of the determinant is going to change. The absolute value will be the same, but the sign will change. All right. So, this is the property phi. The next property is interesting. It uses this particular property to prove it, but what it says is that if you now have two rows which are identical, then the value of the determinant is also 0. Just very remarkable sort of a property, and especially when we look at it, the proof of that is also very fascinating. And this statement is not just confined to that of a row, as we have seen. Whatever we say about a row, in most cases we can also say about the column, and the statement there would be that if two columns are identical, then the determinant of that matrix is also 0. So, let us just look into that. So, the property 6 is if two rows or columns of a matrix are identical. So, identical means that they are same, then the value of its determinant is 0. Okay. So, if two rows or columns of a matrix are identical, then the value of its determinant is 0. Right. So, but how do we show this? Of course, we could look at some examples and say, but more interestingly we could use a property phi. How? Well, let us say we have a general square matrix A. If we believe property phi, then we have that if we interchange any two rows or columns, then the sign of the determinant should change. Okay. But if two rows are identical, if you interchange them, the matrix itself is not going to change, but the sign of the determinant will change. So, this is only possible if the value of the determinant itself is 0. So, let me just write this down. So, the proof is, so consider a square matrix A right, which has identical rows with 2 identical rows. Let us call those rows R I and R j. R I and R j. We know that interchanging the rows R I R j will give same matrix A, will give same matrix A, but from previous property the sign of the determinant changes. That is, that if you had determinant A was the determinant of the matrix A, if you changed the value of the interchange the rows R I and R j, then the sign of the determinant would be minus of this. So, determinant of this would be the determinant of the matrix A, where the sign rows R I and R j are interchanged, but because R I and R j are identical, this matrix is nothing but A. Therefore, we come to a situation where minus determinant of A is equal to determinant of A, which is only possible if the determinant of A is 0, all right. So, using the previous property, we want to say here that if you have a square matrix A which identical rows, 2 identical rows, or we can say have the same argument for 2 identical columns, then the value of that determinant is going to be 0. Okay. So, this is also an interesting property because it has many ramifications or many corollaries that we could look at. One of them is interesting, so let me just make a note of that, and that goes back to the definition of a determinant. So, if you think about the definition of a determinant, it says that a determinant is nothing but the sum of the product of rows of entries of one row or column and their corresponding cofactors. What happens if you take the sum of the product of entries of a row with the cofactors of another row? What I am saying is the following. Let us look at a 3 by 3 matrix, and let us say that we have a 3 by 3 matrix. Consider a 3 by 3 matrix as before we use A11, A12, A13, A21, A22, A23, A31, A32 and A33, right. So, these A's, small a's determine the entries of a matrix, and let us say that capital A is cofactor of the entry Aij. Then determinant is nothing but, let us say if you expand along A11, then the determinant is going to be A11 times A11 plus A12 times A12 plus A13 times A13, right. Now, the question is, what happens if you replace these cofactors with the cofactors of these other elements? In other words, what happens if I do the following: A11 is A21 plus A12 times A22 plus A13 times A23. So, what is this value? And in general, we could ask this for other expansions of rows or columns. What happens over here? Well, the idea is, or the answer is, that this is going to be 0, and an easy way to look at this would be to try to go back from this sum of products to the matrix whose determinant is expressed by this expression, and it will turn out that that matrix has two identical rows, and just from the previous property that we saw, if you have something which has two identical rows, then that matrix determinant is going to be 0. Let me write that down. So, that expression A11 times A21 plus A12 times A22 plus A13 times A23. What is this? Now, let us just expand A21. This is A11. A21 is nothing but the cofactor of the element A21. So, there we have minus 1 power 2 plus 1 times the determinant of the matrix obtained by deleting the entire row containing A21 and the column. So, this is A12, A13 and then A32, A33, okay, plus A12 minus 1 power 2 plus 2 times the determinant of the matrix obtained by changing the entire row or deleting the entire row and column of A22. So, that is A11, A13, A31, A33, and similarly the last term is going to be A13 minus 1 power 2 plus 3 times A11, A12, A31, A32. Okay. So, this term is minus 1, this term is plus 1 and this term is minus 1. So, if I take minus 1 outside, then if I write this down, this is going to be A11 times A12, A13, A32, A33 minus A12 into A11, A13, A31, A33, right, plus this term, the last term which is A13 times A11, A12, A31, A32, okay, and then I close the bracket. So, if you now just inspect this, this will nothing but the determinant of a matrix. So, we are sort of going reverse the definition of a determinant. So, if I just say that this is the determinant of a matrix A11, A12, A13, A12, A11, A12, A13 and A31, A32, A33, which was, so the step from here to here was by just expanding along this row, and what we see here is that there are these two identical terms, and just from the previous property we know that this means that this determinant is 0. So, therefore, what this is telling us, if I can just draw this big arrow here, is that for evaluating a product of the entry of a row and multiplying it with the cofactors of another row, the value of that sum is going to be 0. So, this is an interesting property. So, I mean, if you take the sum of the product of entries of a row and their cofactors, that is the determinant. But if you now take replace their own cofactors with the cofactors of a different row, then that sums to 0, and that can be shown using this property. All right. So, that is this. Now, what we want to do is, so this is the next set of 3 properties where we have talked about what happens if you interchange the rows, what happens to the transpose if you interchange the rows and the columns, what happens if something is identical, the rows or columns. Then we have come up with simple ways to say how the determinant of that matrix changes, and with practice these properties become second nature. So, you can look at some operations and see what happens to the value of the determinant. Now, the next set of 3 properties are also interesting. They have to do with what happens if you take some sums or products of the either the entries of the matrix. So, what happens if, for example, you multiply the entire row of a matrix with some number, how does the determinant change? Or if we sum 2 rows of a matrix, how does the matrix change, right? So, these are things that we will look at next. So, these are next set of properties. So, the immediate next set is property 7, and this says that if we multiply, if each element of a row or a column is multiplied by a constant, let us call it k, then the value of the determinant also gets multiplied by k. So, the idea is this, that if you take the entire row, change its value by multiplying every row element by k, or for a column, then the value of the determinant also multiplying with k. And it's how do we show this? So, one way by looking is just by looking at the definition of a determinant. So, you consider expanding along the row which is getting multiplied, that before and after the multiplication, each entry of the row has increased by a factor of k, and so we can take that factor out, and then we get that the determinant itself is increased by k. So, we can look at a let us say a 2 by 2 matrix example to see the case. So, if we say a matrix A, B, C, D, and this element R1, the row R1 goes to k times R1. Okay, so, the matrix becomes Ka and Kb. So, the question is what happens to their determinants. So, the determinant over here, and if instead of looking at the formula AD minus BC, let us just write it down as A times its cofactor, whatever that is, we know it is D, but let us just write it down, plus B times its cofactor, we know it is minus C, but let us just write it down. So, this is the sum. Okay, so, here actually should be C, but we really do not sorry. So, this should be D and this should be minus C, but we really do not worry about this so much. The main idea is you expand along the row AB. Now, here if we also expand along the first row, what is the determinant? It is going to be Ka times the cofactor, which does not change, it is the same, D plus Kb times the cofactor, which again does not change, minus C. So, here this k can be just taken out. So, this is going to be k times A times this plus B times whatever is the cofactor, it's minus C here, D here, and you see that the expressions here are the same as this. So, these two are the same, only thing is k. So, the determinant goes up, the determinant scales by the factor k. So, this is just if you do some scalar multiplication of an entire row, and we can do this for a column also, what we will see is that the value of the determinant is going to change or scale by a factor k, all right. So, this is a property regarding multiplication, and now we want to see what happens if you have a sum involved in the matrix, what happens to the determinant. So, to be specific, we are looking at a property of a matrix that if every entry can be expressed as a sum of two elements. So, if every entry of a row can be expressed as a sum of two elements, then the determinant can be written down as the determinant of matrices which have been found by separating the sums. So, let me just write it down, it may be more clearer. So, the property statement is that if sum or all elements of a row or column can be written as a sum of two terms, then the determinant the overall determinant can be expressed as the sum of determinants and this sum of determinants are of matrices obtained by separating that original matrix. Separating the original matrix. What does this mean? So, let us just look again at a simple example, again a 2 by 2 example. Suppose we have a matrix A plus x, let us say, and B plus y, all right, and then C and D. So, what is the determinant of this? Well, we could try to say, okay, I should point out that this x, because it says sum or all, even if you can't write it as a sum, in some cases this x could be just 0. So, it is not that we need all of them to be written as sum. The sum could be such that the decomposition could be in terms of a plus 0, for example. So, what we want to say is that the determinant of this is equal to the determinant of a matrix obtained by, so this is the decomposition that we are talking about, plus x, y, c, d. Okay. So, this is how we have decomposed one determinant into a sum of two determinants, just because the elements of one row were able to be decomposable into two elements. All right. So, this is what we mean by the statement. And how do we show this? We can show this again directly by just by the definition, again as we have done previously, by expanding along the row, and because now each when you look at the sum, each product is going to have a plus x or b plus y or something like that, then we just split those, and then whatever we are left, the two products can go back to its own set of determinants. So, let me just write down what I just said. The idea is as follows. So, if you look at the determinant over here, and again like in the last example, rather than looking at the formula a plus x times this minus c times b plus y, let us say that we are expanding along this row and we have a plus x times its cofactor plus b plus y times its cofactor. Now, we know actually that this is nothing but d and this is nothing but minus c, but in general we do not know, and that so in general we do not really need to know what those are, because we are just expanding and we are concentrating along these terms. So, this can be written as A times D plus B times minus C plus, so this is one set of terms, plus x times D plus y times minus C. Now, if you look at these, this is nothing but, the first is nothing but the determinant of this term, and the second is nothing but the determinant of this term. So, this is a sum of two determinants which are determinant of matrix A, B, C, D plus determinant of the matrix X, Y, C, D. Right. So, we have expressed one determinant in terms of sum of two determinants. That is what is meant by this meaning sum of determinants. All right. So, this is this property which, to state again, says that if we can decompose the sums of a row here we have considered, but also of a column in terms of a sum of two terms, then the determinant can be expressed as the sum of two determinants. Okay. And then the next property, which is the last in the series that we are going to talk about, is in some sense the opposite of this, and what that says is that if you look at a matrix which has a certain determinant, and if you add two rows of the matrix and replace one of the rows with them, then the determinant is going to be unchanged, and that uses, to show that, would be saying that we use this property and also the property that we had seen earlier about two identical rows, meaning that the determinant is 0, and whatever we say about the rows also holds for the columns. So, let us just see what that property is. So, this is property 9, and the property 9 is that if we have, if each element of a row or column is replaced by a sum of that element and an element of another row. So, the idea is that each row, each entry will be replaced by a sum of that element and the element of other row. So, the same other row is considered, or column. Then the value of the determinant remains the same. So, let us look at a 2 by 2 example to illustrate this. Suppose we have a matrix A, B, C, D, and we replace the first row R1 with R1 plus R2. Then this is going to give a matrix A. So, we are replacing A with A plus C and B with B plus D and C and D. So, another question is, what is the determinant of this and what is the determinant of this? So, determinant over here is AD minus BC. Determinant over here is, how do we find the determinant of that? Well, just like we saw in the previous property, the determinant of this matrix can be replaced as the determinant of the matrix A, B, C, D, right, because this are two sums. So, we have plus determinant of CD, right. So, this is from the previous property, and if you look at just this matrix, we see that these two rows are identical, and so this determinant goes to 0, and what we are left with is nothing but determinant of A, B, C, D, which is the same as over here, and this we see for a 2 by 2 matrix, but it holds true in general for a general n by n matrix. So, with this we have finished the 9 properties of determinants that we wanted to explain. For each of them we have looked at some examples. What we will do is to look at some problems which use this property in next set of lecture, but the idea for looking at these properties are that okay, we are going to have to evaluate some determinants. We could use directly the definition, but what we are doing here is by noting some simple determinant calculations and some properties, we can manipulate determinants of relatively complicated matrices in a simple fashion. So, we could obtain the determinants of relatively complicated matrices, simplify them, and this simplifying idea is behind the goal of looking at these properties. So, with that I thank you for your attention, and I hope that these properties add a different layer perspective to your understanding of determinants. Thank you.